Okay guys, so we're going to talk about some more trig identities here. There's not really anything new necessarily in today's lesson, but I want you to see some examples of maybe some harder trig identities. So I want to start with sort of an interesting problem that sometimes comes up. Let's consider the following question. Express every trig function purely in terms of, let's say, cosine of x. Okay. So when I say every trig function, I mean all six: sine, cosine, tangent, cosecant, secant, cotangent. So let's try that. Obviously, cosine of x is sort of itself already expressed in terms of x, in terms of cosine x. There's nothing to do there. But how can we express sine of x in terms of cosine of x? Well, we do have an identity which relates sine and cosine, and that's the standard Pythagorean identity. Sine squared x plus cosine squared x is equal to 1. Well, if you think about it, you can solve this equation for sine of x, and you'll wind up with an expression for sine of x which involves only cosine. So subtract 1 from both sides, and I have 1 minus cosine squared x. And then to get the sine x by itself, in other words, to get rid of the square here, remember this means sine of x quantity squared. So in order to isolate sine of x, we take the square root of both sides. Now I do have to, unfortunately, put kind of a plus or minus here in the square root. This is actually the answer. This is a formula for sine purely in terms of cosine. You might wonder what's up with the plus or minus. Technically, which one you use depends upon which quadrant you're in. I don't want to get too much into it, but basically, depending upon what angle x represents, you'll have to take the positive root or the negative root to make this formula actually work. Okay, so let's try. So that's sine of x in terms of cosine. Let's try and do the others. So let's see. So what else do we have? We have tangent, right? So what can I say about tangent? Well, I certainly know that tangent of x is equal to sine of x over cosine of x. But remember, I want to express tangent purely in terms of cosine, not sine and cosine. Well, what I can do is I can actually replace this sine of x here with this expression that I just obtained over here. That would give me plus or minus root 1 minus cosine squared x all over cosine of x, right? Okay, so that's expressing tangent in terms of cosine alone. Let's take a look at maybe, say, secant of x. That's pretty easy. The reciprocal identity says that secant of x is 1 over cosine of x. So that's a formula for secant purely in terms of cosine. Very straightforward. How about cosecant of x? Well, cosecant of x I know is 1 over sine, and I've already established that sine is given by this formula here. So that would give me 1 over plus or minus root 1 minus cosine squared x. Okay, and then I suppose last but not least would be the cotangent function. So what can I say about cotangent? Well, cotangent I know is cosine over sine. And once again, I can replace the sine here with this expression. So I have cosine of x over plus or minus root 1 minus cosine squared of x. So that's expressing all 6 trig functions in terms of cosine alone. Interestingly, you can do this with any trig function. You can express all of them in terms of sine. You can express all of them in terms of, or I think you can, in terms of tangent and the others. I'd have to think about it carefully, but I believe it's possible to do it for any of them. Okay, so moving on, that's sort of an unusual problem. Let's try a more standard trigonometric identity problem. So let's try to prove the following trigonometric identity. Cosine squared x over 1 plus sine of x minus 1 is equal to negative sine of x. So, you know, this is a little bit tricky. It's not super clear what you should do here. I suppose that one thing you might think about is you might notice that the left-hand side has 2 terms, 1, 2, and the right-hand side just has one term. And so therefore, maybe we should be combining these two terms into a single term. That would mean treating the 1 as a fraction, like 1 over 1, getting common denominators between the two fractions, and then smashing them together. That's all fine, although I will say it doesn't really lead anywhere. Let's just have a look. If you do that, it doesn't really produce anything nice. What you would obtain is this: cosine squared x over 1 plus sine x minus, thinking of this as 1 over 1 and then getting a common denominator would give me 1 plus sine x over 1 plus sine x. Okay? So that's the left-hand side of the equation. Now, if I combine these two fractions, I obtain cosine squared x. And be careful, this minus sign is really being applied to both terms of the numerator here, so make sure you subtract both of them. Minus 1 minus sine of x all over 1 plus sine of x. You can do that, but you might notice that, this just doesn't really clean up in any obvious way. There's maybe not anything that you could obviously do. There is one thing that might stick out at you. You might notice the cosine squared minus 1. You might think that that is something due to the Pythagorean identity. Let's recall the Pythagorean identity, which says that sine squared x plus cosine squared x is equal to 1. If you solve this equation, or rather, I suppose one way of doing this, you could solve this equation for cosine squared x and write cosine squared x is equal to 1 minus sine squared x, and then make that replacement for the cosine squared. So in other words, replace cosine squared with 1 minus sine squared x. That'll give me 1 minus sine squared x minus 1 minus sine x over 1 plus sine of x. Right, I've just replaced cosine squared x with 1 minus sine squared. And the reason that's sort of interesting is that the 1's disappear. So that just gives me negative sine squared x minus sine x over 1 plus sine x. And you might sort of be looking at this and wondering, boy, what could you do? Well, there's actually a common factor in the numerator of sine. Actually, maybe we should pull out negative sine. That might make things sort of even nicer. Negative sine x. When I remove negative sine x from this term, I'm left with just positive sine x. And when I remove negative sine x from this second term, I'm left with nothing, so I just have a 1 over 1 plus sine x. Then you might notice that this factor here is actually equal to that factor, so they cancel. And that leaves you with negative sine x, which is actually the thing that we were trying to prove. So that's how that goes. I think that when I first started out doing it, I said that perhaps combining these two fractions right away was not the best idea. There is another way of doing it. So let's sort of go back to the very beginning here. So this is our first step here. I think perhaps this can be done a little bit more quickly if you just right away. So here's at least a different way of doing it. You could replace cosine squared with 1 minus sine squared. So 1 minus sine squared x over 1 plus sine x minus 1. And then you could recognize that this is actually the difference of two squares, so it actually factors as 1 plus sine x times 1 minus sine x over 1 plus sine x, all minus 1. And then you could say that, oh, this factor cancels with that one, and you're left with 1 minus sine x minus 1, which of course just leaves you with negative sine x. I think that's a much faster way of doing it. They both get you there, but I don't know. Okay, so that's two ways of doing that problem. Let's do one more. So let's try. This is sort of going to introduce sort of a new technique. So the trig identity I want to prove is secant x minus tangent x is equal to cosine x over 1 plus sine x. Okay, so how would we prove this? I recommend you actually start with the right-hand side and try to transform it into the left-hand side, basically because the right-hand side is more complicated. Generally speaking, you should start with the more complicated side. So let's just copy the right-hand side. Here it is. What in the world can you do here? Really, there's nothing. I mean, you can't split the fraction. Remember, this is not equal to, cosine x over 1 plus cosine x over sine x. That is not true, right? Like you can't split this fraction when the addition is in the denominator. There's not really anything obvious you could do. There is kind of a trick. When you see this kind of expression, 1 plus sine x, not 1 plus sine squared x, but like just plain old 1 plus sine x, sometimes there's a little trick that works. If you multiply top and bottom by 1 minus sine x, I guess you might call that like the conjugate or something. If you multiply top and bottom by 1 minus sine x, something interesting happens. In the numerator, I'll just write, I won't really distribute the cosine x. There's not really much of a reason to. But in the denominator, if you multiply all of this out, 1 times 1 and 1 minus sine x and all that, something nice happens. You get 1 minus sine x plus sine x minus sine squared x. And the two middle terms cancel out, the minus sine x and the positive sine x. And that leaves us with cosine x times 1 minus sine x over 1 minus sine squared x. By the way, you could have jumped directly from here to here if you recognized that this denominator here was the product of a sum and a difference. So the multiplying out will give you a difference of two squares, but you don't have to know that. And then hopefully you recognize that 1 minus sine squared is actually cosine squared. So this is cosine x times 1 minus sine x all over cosine squared x. Okay, that's cool. But now we can do a bit of cancellation, right? A copy of cosine x here will cancel one of the two copies of cosine x in the bottom. So that leaves us with 1 minus sine x over cosine x. And then if you remember, what we're trying to get to ultimately is secant x minus tangent x. That's two terms, so it stands to reason that we should try to make this two terms. In other words, split the fraction. So I have 1 over cosine x minus sine x over cosine x, and 1 over cosine, that's secant x, and then sine over cosine, that's tangent x, and that's the answer. You can, if you want, try to start here and then convert it into this, but I think it's a little bit harder. This is probably the easier way to go. Okay, so as I said, not much new in this video, just a few more examples. The one thing to watch out for is sometimes when you get stuck, you can multiply top and bottom by the so-called conjugate. If you see a 1 plus sine x, try multiplying top and bottom by 1 minus sine x, for example. Often nice things happen. Okay.